little more about the logistic model. Why does it behave as it does? If we want a little bit more of an algebraic justification, it's not hard, and it's really good thinking about thinking qualitatively about algebraic formulas. Um, so we've got our model a over 1 plus b e to the minus rt, and there's some claims we can make about what kind of y values we could get out of that. There's a symmetry claim, which will be the last thing I do, because it's just a tiny bit more involved. And then there's claims about what happens when I go way to the right, the idea that it has an asymptote, and the claim is the asymptote is A, and the fact that when I go fairly far to the left, it's accurately modeled by exponential growth. Okay, so let's look at the bounds first of all. E to the minus rt, always a positive number. Okay, oh, and B, we're going to assume here that A and B and R are all positive. Okay, and it's going to be much weirder, especially if B can be negative. So that's an important thing. So this is always positive. Any exponential is positive. Times positive is positive. Plus 1. So that's a positive number, and it's bigger than 1. So I'm taking A, and I'm dividing it by something bigger than 1. So I'm certainly getting at a positive number, and it's going to be between 0 and A, in fact. So that's why it will always be between 0 and A. So 0 less than Y less than A. And it'll be properly in between, because that's not going to die. And so it'll never be exactly A, and it'll never be exactly 0. But what happens if you put in like a large positive t? So that's this one taken care of. If t is large and positive, it's a really good example of qualitative thinking and think about end behavior. If t is large and positive, okay, then RT is going to be large and positive. And if R is a small growth constant, just go further out in t to make sure that RT is really large and positive. Okay, RT is large and positive. Then minus RT is large but negative. So you can even see that. Yeah, pretty much. Okay, and so now I'm taking e to a big negative number, so like e to the minus 100. Okay, that's 1 over e to the 100, or 1,000, or 200, or 500. These are going to be very small, but positive. Very, very small if I want them to be. So as t goes way, way out in this direction, yeah, here's t and here's y. As t goes way, way out, big enough, far enough out to make RT big, then this guy is going to be super small, close to 0. Okay, well, B might be a somewhat big number, might inflate it a bit, but just go further out in t. You will be able to make this whole thing. So B e to the minus RT is small. Okay. Now 1, though, you can't do anything about. If you take 1 plus a super small number, then this whole thing is going to be very, very close to 1. Okay. If you don't believe me, if you're not used to this kind of analysis where I'm just talking about big, small, positive, negative, that kind of thing, just plug in some numbers. Maybe look at the example we had before, and just stage by stage put in t is big, and big enough so that RT is big, and then just trace it through, calculate each stage, and verify that, yeah, that's a small number, and this is very close to 1. And so A divided by 1 plus nothing, basically, in Essential, is going to be very close to A. Okay, so that shows us that, yes, this asymptote is exactly given by this number, as long as we write it in this very standardized way where this is 1. Okay, otherwise it'll just be this over this if I forgot to make this 1. But this is nice to have a 1 here so that this is just the asymptote staring at us. Okay, so that's cool. So that's that claim. Now, what about t large and negative? Same kind of analysis. Okay, let me actually rewrite it. It's awfully over-decorated now. Okay, so now t is large and negative, meaning its absolute value is large. So it's very far to the left on the graph. Okay, so RT is also large negative. Minus RT is now large positive. Ooh. Okay, e to a big positive number is going to be very large. Okay, so for example, it could be like e to the minus 100 or something like that. Okay, that's e to the 100. Boy, that's really large. It's really huge. Okay, so 1 plus e to the 100? Now who doesn't matter? The 1 doesn't matter. So it's as if this isn't there. It's a very common feature that in one situation, this guy didn't matter and the 1 was dominant. In the other situation, the 1 doesn't matter and this guy's dominant. So I'll just squint and just say, hey, It's not like the 1 isn't even there. To a very good approximation, 1 plus e to the 100 is really close to e to the 100. Okay, so what happens if I just erase that? If I'm in the situation where I can erase that? Oh, then that becomes a over b, and then 1 over e to the minus rt is e to the rt. Aha, so it's exponential growth with this growth factor, which is what we were advertising in the other video, that sort of characteristic interest rate kind of growth factor, and then times a over b as the multiplier. Okay, so that's what happens that's why as you go to the left, it really is just ordinary exponential growth. It's in the middle where these guys are of the same order of magnitude where you get the transition from the exponential growth to, hey, I'm ramping out and approaching the asymptote.